Good evening, everyone. As we had discussed in the last class, how one can find the component of a given vector. In addition to that, we had said about the component of a vector is not a scalar physical quantity. However, the magnitude of a given vector is a scalar physical quantity. Today, we are going to discuss how and why. To understand this, we may take the help of transformation in 2 or 3 dimensions. But right now in this class, we are going to take in 2 dimensions. There are transformation under rotation, transformation due to reflection of coordinates, and parity transformation. But in this class, we discuss transformation under rotation, however, in 2 dimensions. As I have told earlier, let us say there is rectangular coordinate system, you may call it Cartesian coordinate system. So take it as xy, you may call it xy plane as well. Let us take a vector like that. So this is a vector R and its modulus is like that. Take here junction as origin, here the point P, head of the vector, say x, y. This is the tail of the vector at the origin. Now, we have to take here x component of this radius vector Rx as x minus 0. So this is as x, and y component y minus 0 as y. As I had told you earlier, we have to take transformation under rotation. For this, we have to fix the origin. We may alter the origin, but for convenience, keeping the origin fixed, and we rotate the axis through an acute angle. Let us see here. X prime, y prime, rotated through an acute angle theta. keeping the origin fixed. Now here x, y are taken as x coordinate of the point P or abscissa, and y as y coordinate of the point P or ordinate. So, just for the sake of revision, what is x component, y component of a given vector? As we had discussed or said something about in the last class, as knave definition of the components are scalar physical quantity. But today we are going to prove it true definition under rotation. We will see if the quantity will not change under any transformation, then we define the quantity as a scalar. If it will change, then we cannot say the quantity is a scalar physical quantity. X coordinate, it is a distance from y axis parallel to x axis, and y coordinate is a distance from x axis parallel to y axis. So, look at here, if we draw like that, this is x and this is y. So, here x axis is perpendicular to y axis. So, this is parallel to x axis, automatically it comes out to be perpendicular to the y axis. So, one cannot define x coordinate as perpendicular distance from y axis, because we have oblique coordinate system as well. Look at here. Say this is not right angle. So, theta is here an acute angle. So, still we have a point and we may define x and y coordinate. Still the definition runs parallel here. Distance from y axis parallel to x axis is the x coordinate, and distance from x axis parallel to y axis is called y coordinate. Customary we write starting with the parenthesis, firstly the x coordinate with y component separated by comma, and then close with the parenthesis. So, if we define here the perpendicular distance from y axis parallel to axis as x coordinate and y coordinate as perpendicular distance from x axis parallel to y axis, then here we have objection. That is why definition runs parallel. So, we always say parallel, never say perpendicular. However, it comes out to be perpendicular altogether, definitely so. Okay. So, here now again in this coordinate system x prime y prime, the point is same here. So, we write like here x prime y prime, draw like that here. So, this is y prime, and like that here this is x prime, equivalently you may say here x prime. In addition to that, draw perpendicular from this is also perpendicular, draw the perpendicular, and now again the perpendicular from here. Now extend from both the ends. Look at here, these two lines are parallel, so this is a transversal, so this angle is theta, then it is also theta. Look at here, now it is right angle, then also it is a right angle, so this angle comes out to be 90 degree minus theta. Look at here, this is also 90 degree, then it comes out to be theta. Now from the figure, so this is the x here, and this is say P, Q, R, S, T. So x is our Q. If we subtract QR from our, then it is equivalent to, or you may call equal to, our Q. So look at here, x is equal to this distance r, this is the x prime cos theta from right triangle ORS, x prime cos theta. So subtract this QR, so QR, look at here, y prime, this is the angle, then PT comes out to be y prime cos theta, then TS comes out to be y prime sin theta. So we have to subtract it from x prime cos theta, y prime sin theta. Now the y is equal to, look at here, this is SR, because it is a rectangle, is equal to TQ. So what is SR? X prime sin theta. Look at here, x prime sin theta. And look at here, PQ is y, look at from the figure, or from right triangle OQP. So PQ is y, so this sum of PT plus TQ, TQ is equal to SR. So x prime sin theta plus here y prime cos theta. Now look at x is the x component of the radius vector, y is y component of radius vector Rx. So what about x prime y prime? So you may take it OP as R prime vector. Look at here, R prime vector, and its modulus is R prime modulus. So here x prime y prime. Similarly, our x prime is x prime, our y prime as y prime. So the components of a vector are related. Look at here. So it is very clear from this relation is that x is not equal to x prime and y is not equal to y prime, means x component in xy frame is not equal to x component in x prime y prime frame. That is why the component of a vector is not a scalar. This is the proof. Now then, what about modulus? Of course, let us say here modulus of vector r is equal to modulus of vector r prime. So now we have to see from this here, we may prove it by using these relations. Now look at here. Mod r is equal to mod r prime is equal to square root of x square plus y square is equal to under root x prime square plus y prime square. Let us prove it. So take under root x square plus y square is equal to under root x prime cos theta minus y prime sin theta whole square plus x prime sin theta plus y prime cos theta whole square. So square of these two terms, minus of 2 times of that, square of these two terms, plus of that. Look at here, x prime cos square theta, here y prime cos square theta. Look at here, x prime cos square theta, here x prime sin square theta. So take it out x prime square, so in bracket cos square theta plus sin square theta, or you may call it sin square theta plus cos square theta, then it comes out to be 1. So here we have left with x prime square. Look at it, plus y prime sin square theta plus y prime cos square theta. So y prime square taken as a common, then in the bracket sin square theta plus cos square comes out to be 1. So now we have left with y prime square. Now here 2 times of x prime y prime sin theta cos theta minus here plus twice x prime y prime cos theta sin theta. Then these 2 terms will cancel out. We have left with that. So look at here, this is equal to that. It is automatically very obvious from the figure, because length of this vector is same in both the frame x, y and x prime, y prime. However, vector also remains same, because as we know, a vector will change, either changing in its magnitude or direction or both. So in this way, we have seen here right now, the component of a vector is not a scalar. However, the magnitude of a vector is a scalar physical quantity. Okay.